Hello and welcome to this FCIA Bright Talk webcast on what's new in FC-NVMe-2. This is a webcast sponsored by the FCIA Education Committee, and we will be recording for future playback. Also, the slides for this presentation are already posted on your webcast landing page. You'll see an attachments tab at the bottom of the console if you'd like to download the materials. Our speakers today, we're really fortunate to have a great group of very knowledgeable presenters for this topic. Craig Carlson is a senior technologist with Marvell's semiconductor division. He's an FCIA board member, also vice chair of Insight's T11, and chair of the FC-NVMe working group. We also have Marcus Thordal, who's a principal solution architect at Broadcom. He leads the BSN Solutions Lab. He spends his time validating storage technologies and works with customers to understand their business needs to apply these in combination with defining next generation storage architectures. And I'll be your moderator for today. My name's Mark Jones. I'm an FCIA board member and current president of the FCIA. I'm also the director of tech marketing and performance at the MLX connectivity division for Broadcom. Okay, a little bit about the FCIA. You know, we've been around for a long time. The FCIA has been around for 25 years, promoting Fibre Channel and really being the voice of what is developed in this industry. And so we've been very proud and excited to watch Fibre Channel develop over the years. And the FCIA is represented by most of the leading companies in the industry, and really is guided to help secure the future and performance of the technology as we go into the future. And this is proven out by the tremendous adoption we have had through the years and continued success with customer purchases of Fibre Channel products. We're up to, at this point, about 142 million Fibre Channel ports that have been purchased. And we have a whopping 43 million ports still in use today by some estimates from Clowen Research. So things are going great for Fibre Channel. You know, some of the key tenets of Fibre Channel are, you know, Fibre Channel is purpose-built. It's a purpose-built network just for storage. It's not shared for any other purpose. So it can really focus on just making sure that Fibre Channel data is handled securely and correctly. It's a complete network solution defining both the physical and network infrastructure and the data transport protocols. Some of the key parts of that are, you know, lossless. So by nature, Fibre Channel is a lossless network and congestion-free. It uses a credit flow-based system to ensure delivery of data is as fast as possible to the destination, and buffers can receive without dropping frames or losing data. Multiple upper layer protocols. So Fibre Channel is a transport and autonomous to the protocol mapped over it. So it can include SCSI, TCP/IP, SCON, NVMe, and whatever that we need to add to the future can run over that. Multiple topologies. So Fibre Channel can support point-to-point, so basically connecting two devices directly together, or switch fabric, where we can have a myriad of devices connecting in to form a fabric for easy connectivity. Multiple speeds, so products are available supporting 8 gig, 16 gig, and 32 GFC speeds today, and always backwards compatible 2 generations. Inherent security, communication can be protected with access controls such as port binding, zoning, LUN masking, full authentication, and encryption. So lots of security. And then really foremost is resiliency. Fibre Channel supports end-to-end device-to-device flow control, multipathing, routing, and other features that provide load balancing, the ability to scale, and self-healing and rolling upgrades. So our agenda for today for this What's New in FC-NVMe-2 includes background, Fibre Channel terminology, Fibre Channel basics, the problems, but I thought it was reliable. We'll try to answer that question. And then we'll get into the solution, and then we'll show you some in-depth look at sequence level error recovery examples, and then we'll wrap up with a summary. So please hold your questions to the end. We'll be answering those questions at the end of the broadcast. Also, we typically take the questions from each of these and create a blog, a Q&A blog for the presentation that'll be available for later reference after this is all over. Okay, so now I'd like to turn this over to Mr. Craig Carlson. Craig, it's all yours.
Right, thank you, Mark. So a little bit of background. So, we're not going to do a tutorial Fibre Channel here. If you do want to get a tutorial for Fibre Channel, we do have some other more basic webinars that you can view. So we're just going to I'm just going to give a quick background on some of the Fibre Channel terms and structures that we're talking about in this presentation, and also some background on the problem that we're looking at. So, initial NVMe Express over Fabrics had a solution that was determined if there's any type of error. This meant the entire connection between a specific controller and a specific storage device or array or what have you. We call this the big hammer because it's a very, very basic error recovery. Actually, I wouldn't. It's a very, very basic error recovery mechanism. You disconnect and reconnect, and anything that was outstanding would have to be resent because you would lose anything you would lose any requests that are in the queue. So you'd have to go back and figure out what devices or what commands you have to resend. The NVMe over Fabrics 1.1 added the ability to disconnect a single I/O connection, but this still is what we consider a big hammer because it still requires you to go back and figure out what you need to resend because the queues for that single connection would also be removed. So a little bit of terminology. So for the lower level Fibre Channel communication and control, we have two structures. First is the basic link services, and these are very low level command protocols that do basic things. In this step, we'll be looking at something called the ABTS, which is the abort sequence, which it tells the devices to abort a specific sequence of frames, and I'll get into what that means in a second. And then we have the ELSs, which are higher level control, and there are multiple ELSs for multiple different functions. We have ELSs for log in, log out. We have ELSs to check error counters, link status, things like that. And in this particular deck, we'll be looking at one called the REC, which is a error recovery for the SCSI protocol. So a little bit of basics on how the Fibre Channel works. So Fibre Channel the Fibre Channel transfer is made up of three fundamental constructs. There are frames, sequences, and exchanges, and I'll get into each of these in more detail. So a frame is basically, in other protocols, what would be called a packet. A frame can be up to 2112 bytes, and each frame consists of a header, which contains the routing information, the source and destination, as well as other control information. The payload, of course, where the data is, and then a CRC, which is a check to make sure that the data and header are correct when received on the receiver. And then frames are bundled into multiple groups called a sequence. And a sequence is used to send a larger amount of data, up to a powerful multi-megabytes, and possibly even bigger, instead of the single 2112 bytes for a single frame. And then these sequences are then sent as exchanges, and an exchange generally maps to a command response for a specific protocol. Now, all protocols are different, so not every single protocol may do this, but most of them do this. Most exchanges are mapped to a command response. And the individual frames within a single exchange are guaranteed to be delivered in order, but individual exchanges may take different routes to the fabric. This is due to multipath routing, which allows the switch to use the most efficient path for any specific command. So the problem that we're looking at, we have a command, read command, and we have a loss during the command, and we can lose the command or the response. Then, with the current or the initial FC-NVMe, you would get an NVMe timeout, and you would terminate the association, which would start sending the abort frames I talked about to terminate different sequences, and then you would have a disconnect. And this would basically remove all the queues and outstanding commands and responses for that specific connection. And then you'd have to go back and recreate the whole thing again, and then to go and try to figure out where you left off. So that means that you're trying to drop back to the protocol or the upper layer error recovery. In FCP 234, the error recovery was based on tape operation, and also was designed before exchange-based routing became popular. So frames in those days, frames were always delivered in order, and exchanges were always delivered in order. And then we came exchange-based routing, which made that type of, especially for devices that are not tape-based, that type of error recovery, the old SCP 234 error recovery, made it not viable. And so, you can have a timeout, but the frame can become out of order with the recovery mechanism, which kind of invalidates the recovery. And so, short of that, what you have is a big hammer that I talked about for FC-NVMe, which builds a lot of the connections, because you can't really use the SCP-4 error recovery because it really does not handle out-of-order exchanges very well. So you may be asking yourself, but I thought this was all reliable. The protocols are designed to be reliable. The switches are designed to be reliable, but we live in a world with lots of stuff happening, and bit errors do happen. They are lower than you might see for the theoretical numbers, but they still do happen. And you can also, of course, have hardware or software errors that also can cause frame loss. So what can cause bit errors? Well, we've all heard the cosmic ray story, and not in the 90s, IBM did a study that suggested that a computer memory experienced about one cosmic ray-induced error per 256 megabytes per month. And that was in the 90s. With the larger memories we have today, that could potentially be a larger, higher, more frequent error. And then you also have a possibility of radiation from the local environment. And for modern chips, the component makers are very careful to make sure that the components sourced, the solder and things like that, do not have any inherent radiation that could cause errors. And then probably the most common type of error source would be RF and power line noise from local equipment, and even the power company, even changing generators at the lower power company can induce a low frequency noise that can disrupt some limit. And of course, there are software hardware bugs, and I think we all have probably experience with those. The common specified bit error rate is 10 to the minus 12, 10 to the minus 15. Though the actual error rate you will see is much lower than that. But that's what the specifications usually say. So how did this work before? There is some limited error recovery on the link. There is low error recovery, and most of the higher speed interconnects today, especially 32 gig, 60 gig, 64 gig, have something called full error correction of FEC. FEC is a mechanism that has a mathematical formula that allows you to recover multiple bit errors in a specific block of data. Of course, the FEC does have a limit of how many errors it can recover. So if you go over that, then you can actually start seeing errors in the actual data received on the receiver. And then the protocol levels do have recovery mechanisms, both SCSI and NVMe, which I did talk about NVMe, and SCSI has one too. But both of these protocol mechanisms are not fast to low level. They are more high level, and they're kind of cumbersome. They can recover the errors, but the recovery time can be in the tens of seconds instead of like milliseconds, like you might want to have. So for the solution, I will then turn this over to Marcus, and he can tell you all about that.
Thank you very much, Craig, and thanks for getting us up to speed here. Yeah, so I want to jump off, or how you say, continue from where we are here with really what is the solution that we're looking at here. And obviously the intent here is to make sure that the upper layer protocol, or the protocol layer, does not need to perform the recovery. And as you talked about, I'm sure everybody's very familiar with SCSI timeouts, which are, generally in default to like 30 seconds on your operating system, meaning that the recovery at the protocol layer takes a very, very long time. So the intent here is really to make the error recovery happen at much lower level, and therefore have the recovery happen much quicker, and also to the extent that a protocol layer never knows that there was error recovery happening. And so to do that, the solution is basically done by being able to perform the recovery within a given exchange, and we call that sequence level error recovery. In a few slides, we'll go through the semantics of the process in some examples. But first, let's start with a couple of definitions. So the first one is the flush request and response. This is a basic link service, or BLS, and it's used to determine the state of an open exchange. You'll see in a little bit how it's invoked, but it's basically used to query primarily from the initiator to the target to say, okay, where are we with this exchange? At what state are we in? And then compare that with the known state and to basically determine if there is a problem. And if there is a problem, go into error recovery. And when we get to the examples, it'll be pretty clear how that works. Then we have the NVMe sequence retransmissions and retransmission response information units. These are basically used to communicate to the recipient to either retransmit data or command, and whether you received a sequence retransmission request. And then finally, we have the RED basic link service. RED stands for responder error detection. So this is sent from the target when the target discovers a sequence level error, and it's sent to the initiator to basically say, error recovery should be started. Upon process login between the initiator and target, they negotiate the support for sequence level error recovery. So first off, so how does flush work and what is it? Well, periodically the initiator polls every outstanding exchange, and if there hasn't been any communication for what's called or what exceeds the flush timeout value, basically it's a default value of 2 seconds, then if the flush TOV is exceeded, then it will basically send a flush to the target port. And then inquiring, okay, where are we with this exchange? What state do you see we're in? The target then responds back with the state seen from the target side. And on comparison, basically the initiator knows if there was a frame that was lost and whether error recovery needs to be done. If we look at the next slide here, there are also situations where a target may have responded to an NVMe command and then does not receive anything, and then the target's flush TOV is exceeded. In that case, the target can also send flush to the initiator to determine the status of the exchange and basically query if a NVMe conf value was sent. As it says here on the slide, the flush does not require initiative to be sent. And then the flush response from the initiator, if the exchange is closed, basically the target knows, okay, then it can release the resources held up by that exchange. For the REP basic link service, again, as I mentioned earlier, this is sent from the target to the initiator port to indicate that a sequence error was detected by the storage port in an open exchange. Then the target port waits for an event, in our case an NVMe sequence retransmission request, informational unit, before doing any additional processing of the exchange. There's no payload or reply sequence to the RED BLS. So now let's look at the different scenarios which apply. I'm going to go over the following examples: long running command, lost command, lost response, lost transfer ready, lost write data, lost read data where it's the last frame that was not received, and then lost read data if it's any other frame but the last read data frame that was not received. And then finally, we're going to look at the example rate or the responder error detection. So let's start with the long running command. And I think what you will see is that once we go through a couple of them, you get a very good idea of how this works. So we have our initiator on the left, target on the right, and the NVMe command is sent to the target, but then the TOV is exceeded on the initiator. It then sends the flush, and the target then responds back with the flush response, basically saying, the exchange is open, and the target, I as a target have the sequence initiative. So it's basically saying, I haven't sent anything yet. I've received your command, and the exchange is still open. And in this case here, there's no recovery required. Next example is the lost command. So in this case here, the host sends a NVMe command to the target. It does not get any response, and the flush TOV is exceeded, so it sends a flush. It receives the flush response, so it basically sends the flush to inquire, okay, what is the state of this exchange? And then the flush response from the target says, well, this exchange is not open at the target, and the exchange is closed. So then the host knows, okay, what I need to do is basically retransmit my NVMe command informational unit and use the same exchange ID and sequence level error recovery qualifier, and of course the command sequence number. And then recovery is done. Nothing was ever detected at a higher level. Communication continues. The next one is lost response. So in this case here, the NVMe command goes to the target. The NVMe response is not received at the initiator. And so the flush TOV is exceeded. And so it sends the flush to the target, inquiring, okay, where are we with this exchange? The target responds back and saying, well, you have the initiative on this, the sequence initiative, and the exchange is still open. And so obviously now the initiator knows, well, the reason is I didn't receive the NVMe response. That was a lost frame. So what it does is basically sends an NVMe sequence request, retransmission request, for the target to resend the NVMe response. And then the target resends the response. And first it acknowledged that it got the sequence request, and then it sends the NVMe response. And the sequence, sorry, the exchange was, the sequence was recovered. Now the next one we have is the lost transfer ready. I'm sure you're starting to get the hang of it here. What's happening is we send the command to the target. The transfer ready is not received at the initiator. And so what happens is the flush TOV is exceeded and it sends a flush to inquire the target, okay, what is the state of our exchange? The flush response says, you know, initiator, you hold the sequence initiative and the exchange is open. So now the host knows, okay, I didn't receive the transfer ready. So it sends the sequence request, retransmission request, and says, you know, can you please send me the transfer ready again? And the target responds to the sequence retransmission request and then sends the transfer ready. And now, upon receival of the transfer ready, obviously, the host can continue and be recovered. Now, the next three scenarios are first the lost write data and then lost read for last frame and if it's any other frame. So again here, initiator sends command to the target. Target responds with transfer ready. The host sends data frames. And at some point, we hit the flush timeout. And so it will send the flush to the target, inquiring, okay, what's really the status of this exchange? The target responds back saying, well, you initiator have the initiative, the exchange is open. And by the way, I received this much data in our example here, 2048 bytes. Data has been received. And so now the host knows, okay, something went wrong. So it will send the NVMe sequence retransmission request and requesting for a new transfer ready. The target will respond back that it received the sequence retransmission request and then sent the transfer ready. And upon receipt of the transfer ready, then the host can basically start writing again, and it will retransmit the data. And then the sequence was recovered. Now the next two examples are both for read. So again here, we have our initiator sending NVMe command to the target, and then the target starts sending data. At some point, it receives the NVMe response without having received the last NVMe data frame, and thereby detects that there's an error. So it will then send an NVMe sequence request asking the target to resend the data. The target then responds that it's received the request, retransmission request, and then it responds with the data. And then, we recovered the sequence. Now the example where it's not the last frame. So we have the NVMe command going to the going to the target. And then the initiator port checks that there's a sequence error in the data received. So it will send a flush with basically the HT bit equal to 1. That's basically telling the target to stop transmission and give the sequence initiative to the initiator. And so then the initiator sends the NVMe sequence request for data to be reset after receiving the flush RSP from the target. The target will acknowledge that it's received the sequence request, retransmission request, and then it starts sending the data again. And basically our sequence was recovered. Now the last one I have here is the sequence level error recovery, for example, read. So as we talked about before, this is the case where the target identifies that there is something wrong. And so what we have here, we have a write going to the target. Target responded with transfer ready. Initiator starts sending data. And then there's basically a sequence error is detected at the target. And so it responds with the read basic link service to the initiator. And then the initiator will say, okay, I'll send a new NVMe sequence request. So basically a sequence retransmission request for the transfer ready. The target responds and then sends the transfer ready, and now our sequence can basically continue where it left off or where it failed, and we can have the sequence complete. So that was really the solution and the examples. With that, I would like to hand it over to Mark again.
Okay. Thank you so much, Marcus. Those are some great explanations. I think we all learned a lot from that. So please, we're going to get into Q&A in just a minute. But if you have any questions, please submit them in your presenter-to-presenter chat box, and we'll get to those in a second. Just in summary, let me just kind of wrap this up, then we'll get to Q&A. So FC-NVMe-2, the standard is published and available via the Insights website. FCP-5 Rev 01 is posted on the Insights T10 website. This is regarding arbitrary loop and class 2 support, which is removed, and sequence level error recovery functionality being added as an optional behavior. Okay, so Q&A, we have a couple questions here. Let me start with this one. In the case of lost write data, if let's say the second write data is lost, then does the initiator retransmit the while exchange from the first write data, or does it pick up from the second write data? Marcus or Craig, any guesses on the answer to that?
So if you mean write, oh, go ahead, Marcus.
No, go ahead, please.
So if you mean write data, you mean the frame, or you mean exchange? If it's a frame, the data is retransmitted so that there is no loss of FLL. If it's an exchange, we're not losing full exchanges. We're looking at the sequences. So I'm not sure if that answers the question or not. Do you have anything else to add to that, Marcus?
No, I think maybe the slides are not completely clear on if all the data, if all the frames within the sequence are retransmitted. I think that's what the question was. Not so much whether it's from one exchange to the next.
It's getting pretty, it's getting very technical. Is there a good resource for somebody to dig into this and figure that out? I imagine the publications that we mentioned.
I think the best thing to do, Mark, and we still have time to answer some of these questions. The best thing to do is if people have questions that we don't get to, we'll try to answer them offline. The resource to look at is the standard, FC-NVMe-2. Now, of course, the standard is pretty dense, so it may be more easier for people to ask questions here. I do see one question here that I can answer very quickly. FC2 has REC and SRR already. Why reinvent the wheel again? And I tried to cover this a little bit in the beginning of the presentation, but let me answer this again. The reason that we can't use the REC SRR, which is the old tape recovery mechanism, is because in the days it was invented, first of all, it was really invented for tape operation. But if it is applied to FCP or a disk drive or SSD operation, then you have multiple exchanges outstanding. Tape usually only has a single exchange outstanding. And when you have multiple exchanges outstanding, those exchanges can be reordered by the fabric for exchange-based routing. And the old SRR, REC SSR mechanism does not work when exchanges are reordered. It basically just breaks down. And so that's why we created a new error recovery mechanism. And just to be clear about what the FCP-5 standard is doing, what we're doing is we're taking the FC-NVMe-2 error recovery mechanism and moving it back into FCP-5. So both FC-NVMe-2 and SCSI will have that newer error recovery mechanism that can handle errors for SSDs, hard drives, as well as tape in an environment where exchanges are reordered.
Okay, that was great. Thanks, Craig. We have another question here. Can you briefly summarize how SLER, sequence level error recovery, with FC-NVMe-2 compares to how error recovery works with SCSI protocol and what the benefit is to the application, database, or user experience. For example, does it happen faster and cause less latency or disruption to the host application because it's not at the ULP level? High-level explanation is fine, thanks.
So basically, the comparison is, it's like, you know, it's almost an order of magnitude faster recovery. When you're relying on the upper layer protocol, you're relying on protocol timeouts, or as we discussed for FC-NVMe, you're looking at a big hammer where either all connections or a single connection is closed. And those type of recovery mechanisms, you're talking about tens of seconds recovery. First you get to the timeout, then you have a recovery mechanism which requires you to go back and recreate the old queue and commands that were outstanding and resend data. For the SLER recovery, this is happening at a protocol layer. This is happening at a very low level layer. And the recovery mechanism can happen within tens to hundreds of milliseconds. So your recovery is ordered of magnitude faster. And the upper layer protocol doesn't even know that anything has gone wrong. If a frame is lost, the lower level SLER recovery recovers it, retransmits the data, and the upper layer doesn't even know anything's wrong. So what you have is a much faster error recovery mechanism. And you know, if you're talking about what it does to databases and things like that, upper level applications, those applications don't even know anything happened. They just see that their data arrived, and they don't know that anything was lost.
Yeah, that's kind of the whole point, right? It's like you are handling this at a lower level so that the user experience is seamless, and that's kind of what we do in Fibre Channel. Okay, we have another question. Can vendors that implement or started to implement FC-NVMe-1 implement FC-NVMe-2 easily? So I guess that kind of talks about how to move to it, what is affected, and what's the rollout plan. Marcus, did you care to?
Oh yeah, go ahead.
Oh, I'm sorry.
Marcus,
go ahead
and answer that one.
Yeah, I was going to ask how does it affect the fabric? You probably know best about that.
So, I mean, there are no requirements for hardware changes to support FC-NVMe-2. And so it shouldn't be hard to adopt for vendors that are already supporting FC-NVMe-1.
And from the HBA and Target perspective, obviously there is more work because you have to implement the error recovery mechanism, but it's not a replacement, it's an add-on. So it's an optional feature, and it's an addition to what exists in FC-NVMe-2. So basically, an existing FC-NVMe-1 device will work with the FC-NVMe-2 device, but of course there won't be an error recovery. And then to move to FC-NVMe-2, a vendor has to implement the error recovery mechanism, which, you know, it's an error recovery mechanism, so there is some work involved, but the nice thing is the way it's set up is it's backwards compatible, so you can negotiate whether or not you support it or not.
Okay, yeah, and there's a related question. Somebody's asking, will it work on the existing hardware, which I believe we just answered.
Yes, definitely.
Yeah. Are there any real-world testing data on use case behavior of FC-NVMe-2? And better, any data to compare it to competing solutions to show the benefits against other NVMe solutions?
Marcus, do you have an answer for that?
Yeah, so I don't have any demonstration testing data yet, but obviously the big difference is going to be, as Craig also went over, whether the error recovery happens at a protocol level, so at the NVMe level, or it happens below. That's really the difference you're going to see. And to my knowledge, there's no other technology that is, has developed this yet. So therefore, you will see a big difference there.
Yeah, it's a little hard to draw direct comparisons to this, but certainly I think what we're doing here is for Fibre Channel, it is a much better approach. The subsystem big hammer approach mentioned before is it's improved upon, so definitely better in our situation. Another question, okay, I just answered that one. With reference to the section covering transfer ready, is there any information on write accelerated environments and the characteristics of NVMe in these scenarios?
So this is a good question, especially in terms of error recovery. FCP is for many implementations write and read accelerated, meaning that there's hardware that handles the FCP data, and both SCSI and for Fibre Channel, both SCSI and NVMe, FC-NVMe are based on FCP, and so this hardware acceleration exists for both protocols. Now, when it comes to error recovery, you don't need error recovery to run at wire speed. You basically you're at a point where things have kind of stopped a little bit, even if it's in terms of milliseconds. For the low-level processing, milliseconds is not, tens of milliseconds or hundreds of milliseconds is not wire speed anymore. But it's a time frame in which a software can process the error recovery, and that's why existing hardware can be upgraded to use this error recovery mechanism, because error recovery is typically done in software for most devices, not just Fibre Channel, but for Ethernet, TCP. There are some exceptions. There are some error recovery done in hardware, but typically error recovery is done in software because error recovery is not trying to be a wire speed process. What it's trying to do is it's trying to recover you to a point where you can go back to the wire speed and go back to the hardware acceleration.
Okay, yeah, that's answered well. Thank you. Let's see. We have this looks like a follow-on to probably the first question on lost data and retransmits. Person says, shouldn't it pick up where it left off, i.e. the data sequence, and not retransmit all the data sequences? Well,
basically, so this is one of these cases where you have to look at specific condition where you're losing data. In some cases, it picks up where it's left off. In other cases, it has to retransmit things, and it all depends. And we'd have to go back and look at the particular slide. I think this is probably a question that's best answered offline, and we can go through some of the different scenarios and show people when it's picked up, when things are maybe retransmitted and when things are not.
Yeah, fair enough. And like I mentioned, we'll create a blog with all this Q&A, and if there are some things that we can dive into a little deeper, we can best do it offline. So please go back to the fibrechannel.org website and look at the Q&A blogs to follow up on this. We have one final question. It's a little aside from the topic, but it is an interesting question. How are the number of Fibre Channel ports sold doing versus Rocky or iWarp, and are the Ethernet ports affecting new Fibre Channel port sales? Well, I can answer that a little bit. I can tell you that Fibre Channel sales are still very strong. According to Quillen Research, they're still moving at about an 8 million ports per year rate. So we have not seen any noticeable decline in recent years. In fact, we've seen an uptick. A few years ago, there was a very strong surge in sales for Fibre Channel, and that trend continues, although it may be tapering slightly from that uptick trend. So in terms of sales, we don't have any indication at all that Ethernet, in terms of Rocky or iWarp as used for storage, is biting into Fibre Channel port sales. I can tell you though, on the topic of NVMe over Fabrics adoption with Fibre Channel, that I think the Fibre Channel industry has done an amazing job of picking this up and delivering complete supported solutions across all operating systems, and now adopted by most major, if not all, storage array vendors. So I haven't seen Rocky or Ethernet anywhere near having that kind of supported solution capabilities from major vendors, and certainly not adopted in very many major arrays at all. That doesn't mean that it's not being used in other places. There could be other environments, maybe smaller storage solutions that people build themselves, that they maybe are using these solutions. But as far as affecting sales, there is no indication at all. And in fact, I would say this is a shining example of how the Fibre Channel industry has come together to develop a standard, bring in vendors that build complete solutions, and bring it to market. So I think that's our answer there. Craig or Marcus, any answer to that you'd like to provide?
Yeah, I can give a little bit of a comment to that. I agree with you that the very strong ecosystem support around NVMe over Fibre Channel is really, how do you say, a proof point of that is that we see with a lot of our customers today that they're either in a POC phase or they're in a early deployment phase, because they can basically start using FC-NVMe across the same physical ports, both on the initiator, target, and obviously the SAN. There's no, discussion or question about, okay, do I need to change the network or the adapters in any way to support NVMe, which is really the case with, Rocky and Ivor. And the customers I've met with who do something, so I'm talking about enterprise customers here, because you're right, there are obviously for certain solutions where, NVMe over Rocky or just Ethernet in general may apply better. But if we look at the enterprise customers, very few of them are doing anything beyond what I would call proof of technology, which is either, direct attached or in and out of one switch. They're not really doing anything in a network at any kind of scale. And so I think that is a good proof point of, how mature the technology is for the enterprise to adopt. I don't know, Craig, if you have an additional comment to that. My comment would be, for the FC ports, we see what Mark is saying. We don't see any decrease. There may be some pickup in Ethernet ports, but it's definitely not affecting the Fibre Channel market right now. The Fibre Channel market continues to go very strong, especially with FC-NVMe. As another transport for NVMe fabrics, we see a large amount of increase from that as well.
Yeah, great thoughts, guys. Those are all good answers. All right. Well, that's all of our questions. Like I said, we'll wrap this up in a Q&A blog and fill in the blanks if we left any. We thank all the audience for attending here, and especially thank our speakers. You guys did a fantastic job of delivering this information. So after this webcast, please, we ask all of you in attendance to please rate this event. We really value your feedback. It helps guide us on what we're going to deliver next. We're on a regular cadence of producing these educational webcasts, and we're getting some tremendous response back that it is in fact valued. So your feedback is very important. As I mentioned, we'll we will post the Q&A blog at fibrechannel.org with all the answers to today's questions. And then follow us on Twitter at FCI News for updates on future FCI webcasts. And then also visit our full library of on-demand webcasts at fibrechannel.org/webcasts. And we have all kinds of stuff out there. We get a very large library of material, and we're seeing that it's very popular for folks to go back and look at this material well after it's been posted. So we find that's a tremendous educational asset to the Fibre Channel and technical community in general. Okay, our next webcast is kind of stepping back a little bit, kind of like our last question. We're going to look at the Fibre Channel outlook for 2021 and beyond. As we're kind of looking at this as a year wrap up and looking forward to what we have in front of us. So we ask you all to please mark this on your calendar. It's going to be December 3rd of 2020 at 10 a.m. Pacific time. And there's a link here provided for you if you want to pre-register for the event. So from all of us, we thank you very much. We all